All right, guys, 8.4, graphing rational functions. Today we're going to do a quick review on what a degree is because it's very important to today's lesson. So just remember, you guys, that if you have a polynomial, that the degree of that polynomial is always the highest exponent that you see. So if you have something like 2x squared plus 3x to the fourth plus, I don't know, x. The degree here of this polynomial is degree 4 because this guy has the highest degree and it is 4. Okay, so that the degree today becomes very important. Okay, so just reminder on that. Now let's get into some rules for today when we're going to graph these things. So the asymptote rules. Remember that an asymptote is just a place where the graph typically does not cross. Now, graphs can cross horizontal and slant asymptotes, okay, and you're going to learn about both of those today. But they will never cross a vertical asymptote. All right, and most of the time they won't cross horizontals either, but there are specific instances where they might. But generally, the graphs want to be close to those asymptotes. So when f of x is equal to a of x over b of x, and a of x and b of x are polynomial functions with no common factors other than 1, and b of x doesn't equal 0, okay, because you cannot have a 0 in the denominator, then there's a vertical asymptote whenever b of x is equal to 0. Okay, so what that's saying is if I have like, I don't know, 2x squared over x minus 1, let's just say, this would have a vertical asymptote at 1 because if you put a 1 in there, you're going to get a 0. So whatever makes the denominator go to 0 is a vertical asymptote. So that's pretty simple to remember. The horizontal case, and at most there's going to be one of these. Okay, verticals there could be multiple, right? But for horizontals, there are only going to be one. Okay, and it happens if the degree of a of x is greater than the degree of b of x. Okay, actually that's when it doesn't happen. I don't know what I'm saying. There's no horizontal if a of x is greater than b of x. So if the degree in the numerator is bigger than the degree of the denominator, there's no horizontal. All right. So in this particular example here, since this degree in the numerator is bigger than the denominator, this one here would not have a horizontal asymptote. But then look at b. If the degree of a of x is less than the degree of b of x, then there's one at 0. Okay, so if I have something like, I don't know, 2x squared over 3x to the third, something like this, then we know that there's going to be an asymptote, a horizontal asymptote at 0, right in here, that it will not cross. Okay, and you can play with this in Desmos and test these rules out. Then for C, if the degree of a of x equals b of x, then it's going to be the leading coefficient of that thing. So let's take a look at what that means. That means if I have something like 2x squared over, and it could have plus x plus whatever. And then I have, on the bottom, I just have an x squared plus whatever, 2x, whatever, da-da-da. Okay, what it's saying is if the degrees are the same, meaning the exponents, the highest exponents are the same, then what it's going to be is the leading coefficient as a fraction. So in this case, that would be 2 over 1, which is equal to 2. So I know on this particular case that I would have a horizontal asymptote that's at 2. So it would be right in there. Okay, and then the third rule here, you guys, is the oblique one. That happens if degree of a of x minus degree of b of x equals 1. Okay, so if you took the a of x and its degree is 1 more than b of x, the equation of the asymptote will be a of x over b of x. Okay, so which means you have to do some long division to figure this out. So we'll get into all that. Here we go. Here's some examples. So for this guy, notice here the equation here that's here. We have x squared over x. So since the degree of the numerator is 1 larger than the degree of the denominator, I know that I don't have any horizontal asymptotes. And since -1 makes the denominator go to 0, I have a vertical asymptote at -1. Then for the second one, notice I don't have any x's in the numerator, and I have an x squared in the denominator. Therefore, I'm going to have a horizontal asymptote because the degree of the denominator is larger. Okay, so that happens at 0. And then the vertical asymptote is whatever makes this thing go to 0. So x squared minus 1, just a reminder, that's a perfect difference of there's a difference of perfect squares, right? So that's going to be x plus 1, x minus 1 when you factor this guy out, which is why we see two vertical asymptotes. One that's at -1, one that's at +1. Okay. So the last example here, we have a vertical asymptote that's at x equals 3 because in the denominator 3 is what makes that go to 0. Okay, and then I know that I have a horizontal asymptote at 2 because these are the same degree, right? The degree of both of these is 1, so the horizontal asymptote is going to act like 2 over 1, which is 2, which is why they have this horizontal asymptote here at 2. Okay, so some steps to graphing. One of the first things you're going to want to do with all of this is find the zeros. Okay, so you want to factor to find the zeros. Draw your asymptotes in. Okay, vertical is whatever makes the denominator go to 0. Horizontal, you have 3 rules that you can refer back to. Step 3, make a table and plug in x values to get the y values out, and then graph the points and connect. So let's do one. So here's example 1. So first of all, what I want to do is I want to factor this completely. So this will be, if I factor this one, the denominator is already factored, but if I factor that one, we'd have 2 things to multiply to give me -6, add to give me -1, -3 and 2, I believe. So x minus 3, x plus 2 over x plus 1. What that allows me to do is it allows me to identify where my zeros are. First of all, if I look here, whatever makes this go to 0 is going to be a vertical asymptote. Okay, because you cannot divide by 0. So in this case, it's going to be a -1. So I have this vertical asymptote at -1. Then I know that the graph is going to cross in 2 places, going to cross the x-axis. It's going to cross whatever makes this go to 0 and whatever makes this go to 0. Okay, so x minus 3, what makes that go to 0 is 3. If I plug a 3 into that, the whole numerator goes to 0, right? And the denominator is something other than 0. So therefore, 0 divided by something is always going to give me 0, right? So whatever makes either one of those factors go to 0 is going to make the whole thing go to 0, and that's going to be a crossing. So x minus 3, we know that 3 is going to be a place where this graph crosses, and then at -2, it's going to cross. Now, the next thing I might want to check is my horizontals. So for my horizontal asymptotes, again, remember the rule, this is degree 2 on the top and degree 1 on the bottom. Okay, so if the degree of the numerator is greater than the degree of the denominator, there's no horizontals. So we don't have to worry about horizontals here. But now I need to graph this, right? So what I need to do is, once I have that, and I've determined where my asymptotes are, where my zeros are, now I'm going to want to graph some more points. So let's plug a couple more things in here just to see how this thing behaves. If I plug a 0 in, that's an easy one. That would make -6 in the numerator and 1 in the denominator, so we're at -6. So at 0, we're at -6. Then I might want to see what happens at 1. So if I plug a 1 into this thing, I get 1 minus 1, which is 0. 0 minus 6 is -6. And then 1 plus 1 is 2, so I'm at -3. So at 1, I'm at -3. And then I already have that other point, right? So we know that we're doing something like this. And you could plug in something else over here just to kind of see what happens next. But this is just going to go off this way. All right, and then I want to see what happens on the other side of the asymptote, right? So on the other side here, let's see what happens when I plug in a -3. Okay, so if I plug in a -3, I'm going to get, so I'm just going to plug it in there. I'm going to get 9 minus 3 minus 6. 9 minus 3 is 6. 6 minus 6 is 0. So at -3, am I at 0? That doesn't make sense. Hold on. -3 squared is 9. Oh, minus -3. Sorry, so that would be 12. 12 minus 6. Watch your signs there like I just didn't. I mean, 12 minus 6 is equal to 6. 6 over -3 plus 1 is -2. So this is -3. So at -3, I'm actually at -3. Okay, so -3, -3. All right, and I know that this is going to kind of approach this asymptote and start to go this way. And I might want to plug in one more point just to see what happens. Like, let's just see what happens at -6, I guess. So at -6, I'd be at 36 plus 6 minus 6. These cancel out, so it's 36 over, and then -6 plus 1 would be -5. -5 goes into 36 how many times? Let's see here, 7 and something. So we're looking at -7-ish. So we're somewhere down in here. Okay, so you can kind of get an idea of what happens there. Is we got something that looks like that. Okay, so that's example 1. And what I'll be looking for here, you guys, is the asymptotes, the zeros, and that you get a couple of points so we have a general understanding of the picture. So for 1b here, let's look at this one. For this one, we have degree 3 in the numerator, degree 2 in the denominator. So notice that our numerator is bigger than our denominator. So let's go back to our rules here. If the degree of A is greater than the degree of B, there's no horizontal. But if the degree of A minus the degree of B is 1, then there is going to be an oblique asymptote. Okay, so I know there's going to be an oblique asymptote here, but I'm not going to worry about that too much here. Okay, so for this one, for 1b, what makes the denominator go to 0 is going to be -2. So at -2, we know that we have a vertical asymptote. We know that we don't have any horizontal asymptotes, but that we do have some kind of oblique asymptote. And for this one, they don't really care that you plug that in, but know that that's going to be the case, that there's going to have that. So we'll kind of see it here when we plug some values in. So let's just do that. Let's go to plug some values in. So, by the way, we know that a 0 occurs at -1, correct? At -1, we have a 0. Okay, so, and the reason I know that is because if I plug a -1 into the numerator, it goes to 0. All right, so let's look at some of these guys. So let's plug a 0 in. If I plug a 0 in, I'm left with 1 over, that's going to be 2 squared. So 1 cubed is 1. 2 squared is 4. So at 0, I'm at a fourth. So at 0, I'm at 1/4. So I'm somewhere in there. Okay. And then I might want to see, I definitely want to see a couple more points here. I know that this is going to, approach this vertical asymptote somehow. So it's going to come in here and go like this. Okay, I know that, but what happens over here, I don't know. So I'm gonna plug a 2 in. If I plug a 2 in, I'm gonna get 3 to the 3rd power over 4 squared. So 3 to the 3rd is 27. 4 squared is 16. So it's gonna be like approximately like 1.5 when I plug a 2 in. So plug a 2 in, and I'm up here. Just kind of doing this kind of thing. And then maybe I'll plug a 4 in just for fun. So if I plug a 4 in, I'll be at 5 to the 3rd power over 6 squared. Okay, so that's 25 times 5 there gives you 125 over 36. 36 goes into 125. Well, approximately, well, a little over 3 times. So let's go at 4, I'm up here somewhere in the threes, the high threes. And I'm not being super accurate, but this is kind of what's happening. It's kind of going off like that. Then we got to look to the left, right? So the left of the asymptote here, if I plug a -3 in, what happens? So at -3, let's figure that out. Or maybe I'll just plug a -4, actually. If I plug a -4 in, I'll be at 3 to the third over 2 squared, which I already know, right? That comes out to 1, a little over 1.5. But I'm going to be in the... I plugged a negative in there, right? So this is going to be negative, so -1.5. Okay, so at 4... At -4, I'm at 3 to the third over -2 squared. Let me think about this here. -4 plus 1 is, -3. So it's -3 to the third. -3 to the third is -27. And then I have -4 plus 2, which is -2 squared is 4. So it's not the same there. So that's 4 goes into -27 how many times? That would be approximately 7, a little less, 6 point something. So let's just look here at -4, I'm at -6 something, somewhere in there. Okay, so I have that point. Then I need to check a couple other points. Let's actually check -3. So I'm just going to erase here just to make a little bit of room. All right, if you plug a -3 into this thing, I'm at -3 plus 1 is -2 to the third over -3 plus 2 is -1 squared. -2 to the third is -8. -1 squared is 1, so I'm at -8. So at -3, I'm at -8. And then we know that this is going to approach this guy. But what happens if I keep going here? Let's do one more. So if I do a -6, maybe that'll tell me how this thing behaves. At -6, we have -6 plus 1, which is -5. -5 to the third over -6 plus 2 is -4 squared. So that's -125 over 16. I'm just going to plug that into my calculator here really quick. So I have 125 divided by 16. So we're at -7.8. So at -6, we're at -7.8. We're somewhere down in here. So it's kind of wrapping around this way. And there's our picture. Okay, so the hardest part about this is determining when to stop. I would, you know what, if you're struggling with that, maybe graph it on Desmos, see kind of what happens. I do need to see your work though, so definitely plug these in. For example 2b, this is just a real world problem with what we just did. I'm not going to take the time to do it here. And then typically I break this into 2 parts, but I'm going to get it all into one lesson here, guys. So the second piece of this is looking specifically at oblique asymptotes, which I've already kind of taught you the rule. So if the numerator is of greater degree by 1 degree greater than the denominator with no common factors other than 1, okay, then I know that I'm going to have a oblique asymptote. Okay, and it's just going to be, we're not going to worry about the remainder, we're just going to take the denominator and we're going to divide it. So we can use some long division there. So notice what happens here when I try to do that. So if I have x to the third minus 1, okay, and take that into x to the fourth plus 3x to the third, how many times, this is just a reminder, how many times does x to the third go into x to the fourth? That would just be x times. And then if I multiply that out, I get x to the fourth minus x. All right, and then if I subtract that, notice that I can't bring anything else down here. So what I have to do is, since these degrees don't match up, I have to have place values. So it's actually minus 0x to the third minus 0x squared minus 1x. Okay, so then I have 3 minus -0, which is just 3x to the third. Okay, so now x to the third goes into 3x to the third positive 3 times. And then this continues, right? So I have 3x to the third minus 3. But again, there's nothing here that I can line that up with because I don't have like terms yet. So I end up with 0x squared minus 3, which is just 0x squared. And so eventually this is going to just go out into a long remainder is what it's going to end up being. So x plus 3 is the last piece that I need. That is where my oblique asymptote is. At x plus 3, which is a line with a slope of 1 that crosses at positive 3. And notice your picture here. We have a y-intercept of 3, and this thing is going up 1 over 1, up 1 over 1. So this is the line of the oblique asymptote. Okay, the vertical asymptote is just what makes this thing go to 0, which is just going to be a 1. So we have an asymptote there. Then you'd plug in these other pieces to find out where your graph is, right? So you'd plug in plug in a 2, plug in a 3, plug in a 4, and then go on the other side of the vertical asymptote and see what happens. All right, so let's do one of these fully out, and then we'll talk about point discontinuity, and then we'll be done. All right, so here we go. For example 3, we have x to the third minus 1 over x squared minus 4. What I would want you to do then for this is consider factoring this thing out. So this is a difference of cubes, and then we have a difference of squares. So for now, since this is a 1, let's not worry about factoring this too much, but let's just at least factor this one so we can see where our vertical asymptotes are. So x squared minus 4 is just going to be x plus 2, x minus 2. Okay, so I know at plus 2 and minus 2, I have this vertical asymptote. Okay, then I know that since this numerator is 1 degree higher than the denominator, that I'm going to have an oblique asymptote. So let's try to figure that out. That's x squared minus 4 goes into x to the third minus 0x squared minus 0x minus 1. Okay, so then I multiply it out, right? So x squared goes into x to the third, x times. Then I'm left with x to the third minus 4x. Okay, so I have 0 here. Then I have 0x. Essentially, I'll go through another round. I'll have 0. 0x minus negative 4x is positive 4x. But then x squared can't go into 4x, therefore I'm done. It's just the line y equals x. Okay, so for 3b, I know that this line y equals x, which is just a slope of 1 with an intercept of 0, is my oblique. Which can be crossed, it can be crossed, but so you'll notice here actually when you start plugging things in that it can cross that oblique asymptote, but it will not cross the verticals. So now it becomes a little more difficult when you're plugging things in a little longer, because now I'm going to plug in, these numbers, then these numbers to see what happens in between, and then these numbers. And I encourage you to use Desmos there as well. But if I do that, for this, let's just plug in some easy things. If I plug in a 1, okay, a 1 to the third is just 1, 1 minus 1 is 0, so I get a 0, right? So at 1, I'm at 0. Okay, then let's plug in a negative 1. Negative 1 to the third is negative 1, negative 1 minus 1 is negative 2. And then if I plug a negative 1 in the bottom there, negative 1 squared is 1. 1 minus 4 is negative 3. So I end up with 2/3. So at negative 1, I'm at 2/3. So at negative 1, I'm up here at 2/3. Okay, and then, and I know that this thing, if it's in between here, this has to approach this vertical asymptote. So what I have is something that looks like this. Okay, and if you don't know that, and that's confusing to you, because this could just go multiple directions here. If I plugged a 0 in, it would kind of help me figure that out. So if I plug a 0 in, 0 to the third is just 0. 0 minus 1 is just negative 1. 0 squared is 0. 0 minus 4 is negative 4. So I'm at 1/4. So at 0, I'm at 1/4. So I actually could make this a little bit better here. At 0, I'm at 1/4. So I got this kind of thing happening. Okay, so that's what's happening in the middle. Now let's look at what's happening on the outside. So if I plug in, make a little bit of room here. Let's plug in a couple more things here. If I plug in a 3, just to see what happens right after that. 3 to the third is 27. 27 minus 1 is 26. 3 squared is going to give me 9. 9 minus 4 is going to give me 5. So 26 divided by 5, what is that? 5 and a fifth. So that's 5 and a fifth when I plug in a 3. Okay, so plug in a 3, I'm at 5 and a fifth, somewhere up in here. Okay, that doesn't really help me yet. I'm probably going to be bound by this oblique asymptote, but I can cross that, but it's unlikely. Let's plug a 4 in, just to see what happens a little bit that direction. I know it's going to approach this vertical, but what happens at 4? So if I plug a 4 in, 4 to the third power, we got 64 minus 1, which is 63. And then 4 squared is 16. 16 minus 4 is 12. So if I take 63 and divide that by 12, I get 5 1/4. So at 4, not much has changed. I'm kind of just a little bit higher than that guy. So I kind of know I'm doing this, and then it's going to probably approach this asymptote. Okay, so I got a couple points in there to help me with that. Then let's go to the other side. If I plug in a negative 3, what happens? So at negative 3 to the third is just negative 27 minus 1 is negative 28. Okay, negative 3 squared is 9. 9 minus 4 is 5. So if I take negative 28 and divide it by 5, I end up with negative 5.6. Okay, so at negative 3, I'm at negative 5.6. So I'm somewhere down in here. All right, let's plug a negative 4 in. If I plug a negative 4 in, negative 4 to the third is going to be negative 64. Negative 64 minus 1 is negative 65. Negative 4 squared is 16. 16 minus 4 is 12. So if I take 65, divide that by 12, I end up with negative 5.4. Okay, so at negative 4, I'm over here, a little bit higher than that other one. And then you can plug in some decimals if you want to see this, but I'm not going to do that. I know that this is going to approach this asymptote, and it's going to approach this vertical asymptote. So that kind of gives me the idea of what's happening in this picture. And I know this is a really long lesson, you guys. Sorry, just bear with me for one more piece. I'll just do example 4a, and then we'll be done. So the last bit is point discontinuity. Basically, if you have, a rational function with a polynomial in the numerator and denominator, and the denominator is not 0, and x minus c, some constant, is a factor of both numerator and denominator, then we know that that is a point of discontinuity. So for example, we have this guy. After it was factored, we noticed that x plus 1 was in common with both. That means whatever makes that factor go to 0, which is negative 1 in this case, is going to have a hole in it. There's going to be a hole in the graph right there. Okay, that'll always be a point of discontinuity. And then we'll just graph the rest of this thing. So this is essentially the graph x plus 2, because those got canceled, with 1 point of discontinuity. So essentially, since negative 1 made that go to 0, I have this vertical asymptote here, so there's technically a hole in the graph. Okay, so let's look at that. So here, if I factored this numerator out there, I would get x plus 5, x minus 1, over x plus 5. These are in common, right? Since those are in common, I know that at negative 5, I'm going to have this asymptote. But what it's going to end up being for this piece, since all that's left is x minus 1, is this is going to act like the graph x minus 1. Okay, so x minus 1 has a y-intercept of -1, and then a slope of 1. So this is going down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1, and boom, right there we have a hole in the graph. But it's going to continue on, so it's going to look like this. All right, and you're done. So that's just an example of this thing called point discontinuity. It might take you a little bit to see this pattern, so you might need to actually choose some things to plug in. But notice if you plug a -5 in, okay, if you plug a -5 into this thing, -5 squared is 25, right? 4 times -5 is -20, minus 5, all over 0. If you plug the -5 in, you get a 0. Sorry, if you plug the -5 in, you end up with 0 over 0. You're dividing by 0. There's a hole in the graph. Once you see that, you can choose values to the left and to the right of that thing. So if you plugged in a -6, you'd have 36 minus 24 minus 5 over -6 plus 5 is -1. Okay, so 36 minus 24 gives you 12. 12 minus 5 is -7. Okay. Sorry, positive 7. 7 divided by -6 plus 5 is -1. So positive 7 divided by -1 is -7, which is where we're at, right? So you could plug these things in to see where this line is, but it'll end up being whatever's left when you cancel those two things out with a hole here. All right, guys, that's all I'm going to do for today. I'll have a homework sheet for you. We'll catch you guys.